Hi everyone, in this recording we'll be going over the applications of matrices and their determinants. Our goal is that by the end of this presentation, you'll be able to use Cramer's rule to solve systems of linear equations, that you'll be able to use determinants to find areas of triangles, and to test for collinear points and find equations of lines passing through 2 points, and that you'll be able to utilize 2x2 matrices to perform transformations in the plane and find areas of parallelograms. And lastly, you'll be able to encode and decode messages using matrices. Now, what is Cramer's rule? If a system of n linear equations in n variables has coefficient matrix A and the determinant of A is not equal to 0, then we can find each of our variables by computing the determinant of each AI divided by the determinant of A, where AI goes up until an, so our last variable. Now, AI is formed by replacing the ith column of the A, our coefficient column, with constants. So we'll go over an example. So we're given a 2x2 version. So we're given the system A1 times x plus B1 times y is equal to C1. A2 times x plus B2 times y is equal to C2. So our coefficient matrix will be the matrix D with entries A1, B1, A2, B2. So those are the coefficients in front of our variables x and y. Now for our dx matrix, so we're solving for, this one will be used to solve for our x variable. So we will delete the coefficients that are from the x column. So we will replace them with our constants C1 and C2. So we see that instead of A1, A2, we have C1, C2. And our y column will remain the same, B1, B2. So that is our dx. Now our dy, to compute the y variable, we will leave the x column the same, so it'll be A1, A2, but this time we will replace the y column with the constants, so C1, C2 instead of B1 and B2. Now to find our variables, we compute the determinant of our dx divided by the determinant of our d, the coefficient matrix, and that'll give us our x variable. And our y variable will be the determinant of our dy matrix divided by the determinant of our coefficient matrix. So now in box 4 we have the steps that we just followed. We wrote the coefficient matrix A and the constants column. Then we computed the determinant of A. Then we replaced one variable column at a time to form our A1, A2 up until an for however many variables you have. Then you can compute the corresponding determinants. And to find those variables, you divide the determinant of your AI divided by the determinant of your coefficient matrix. Now, it is important to remember that Cramer's rule only works when our determinant is not equal to 0. If it is equal to 0, that means that the system has no unique solution. So here we're given two examples, the first one being a 2x2 version. So we have the system of linear equations, 4x minus 2y is equal to 10, and 3x minus 5y is equal to 11. So first we write our coefficient matrix. So A is equal to the 2x2 matrix with 4, -2, 3, and -5. So we compute the determinant of A. So that will be 4 times -5 minus 3 times -2. So 4 times -5, -20, 3 times -2 is -6. So -20 minus -6 is equal to -14. Now for our dx matrix, to compute our x value variable, we will delete the variables that are in the coefficients that are in the x column, so the 4 and the 3, and we will replace those with the constants, the 10 and the 11. So now our dx matrix has the entries 10, -2, 11, and -5, and we will compute the determinant of that matrix, so 10 times -5 minus 11 times -2, and that'll give us -28. Now to find our y variable, we will first need to construct our dy matrix. So we will delete the coefficients that are in the y column, so the -2 and the -5, and we will replace those with 10 and 11, our constants. And now we can compute the determinant of our dy matrix. So 4 times 11 minus 3 times 10, and that'll give us 14. Now to find our x and y variables, for x, that is equal to the determinant of our dx matrix divided by the determinant of our coefficient matrix. So dx, we stated, was equal to -14, and d was equal to dx was equal to -28, and our determinant of our coefficient matrix was negative 14. So negative 28 divided by negative 14 is equal to positive 2 for x. Now for y, we will plug in the determinant of our dy matrix divided by the determinant of our coefficient matrix. So for dy, we got 14, and our determinant for our coefficient matrix was negative 14. So 14 divided by negative 14 is equal to negative 1. So our y variable is equal to negative 1, and the solution is at the point 2, negative 1. Now for example 2, we're given 3 equations with 3 variables. So first we write our coefficient matrix, and that is A, and it'll be a 3 by 3 matrix. And after that, we will compute the determinant of that. So we do that by first, I'll be using the entries in the first row. So it'll be negative 1 times, and then we'll delete this column and this row. The determinant of this submatrix, so 0 times 4 is 0, minus negative 4, so that should be positive 4. Now minus, now we'll use the second entry, 2, so 2, and we delete this column and this row. So the determinant of this submatrix is 2 times 4 minus 3 times 1. So 8 minus 3 is equal to 5. So multiply by 5. And I'm just using the cofactor expansion that we went over in the previous recording. Now we'll use this last entry, negative 3. So minus 3 times, I'll write it down here. Now the determinant of this submatrix, so 2 times negative 4 is negative 8, and the 3 times 0 will vanish. So now simplifying that, we have negative 4 minus, right here, we'll have minus 10. And then negative 3 times negative 8 is positive 24. So negative 4 minus 10 is negative 14 plus 24. And that gives us a determinant of 10 right here. So since it is not equal to 0, we can use Cramer's rule. And then we will repeat the process that we did for the 2 by 2 matrix. But in this case, it'll be the 3 by 3 since we have 3 variables, or x, y, and z. So here's our dx matrix. I replaced the coefficients in the first column with our constants 1, 0, and 2. Now we need to find the determinant of our dx. And then I'll just repeat the process that I did for our coefficient matrix. So first we'll do 1 right here times now the determinant of this submatrix right here. So 0 times 4 is 0 minus 4 times 1, so that'll give us negative 4 right here. Now we do minus this coefficient right here, 2, and we will do the 0 and the 2, this one right here, and the 1 and the 4. So 0 times 4 is 0 minus 2 times 1, so that'll give us a negative 2. Now here we'll have the negative 3 from this coefficient, and we'll use this submatrix right here. Sorry, it's all scribbled out. But now it's 0 times 4 minus 2 times 0, so that is just 0, so that term will cancel out. And we're left with negative 4. Sorry, that should have been a positive 4 because we did 0 times 4, which is 0, minus negative 4 times 1. So this one right here should be negative, meaning this portion right here should be positive, so we'll have 4. And negative 2 times negative 2 is positive 4, so we'll have 4 plus 4 is equal to 8, and that's how we got dx is equal to 8 for that one right there. Now, you can do dy and dz as practice, but since we found dx, we can compute our x variable. So our x is equal to dx divided by d, so we had 8 for our dx, and our determinant was 10, so 8 over 10 is equal to 4 over 5. Now, after computing your y and z variables, then you'll have a solution, and that is at the point 4 over 5, comma, negative 3 over 2, comma, negative 8 over 5. So now we can use the determinant of a 3 by 3 matrix to compute the area of a triangle. So if we're given the 3 vertices, x1, y1, x2, y2, and x3, y3, then we can form our 3 by 3 matrix where our first row will be our x1, x2, x3, so all the x entries. Our second row will be our y1, y2, y3, our y entries. And our last row will be all 1 entries. And then to compute the area, we can multiply it by plus or minus 1/2. So how to use it? So first we list the vertices, we build our 3x3 determinant, our 3x3 matrix, and then we evaluate the determinant, and then we can multiply by 1/2 and make the result positive. So we'll be going over an example. Here we are told to compute the area of the triangle with the vertices 1, 0, 2, 2, and 4, 3. So for our first row will be the x entries, so 1, 2, and 4. Our second row will be the y entries, so 0, 2, and 3. And our last row will be all 1s. So now we can find the determinant. We'll do 1 times -1 to the 1 plus 1, and then the determinant of this submatrix right here, that one. And then now our second, we're doing these coefficients right here are 1, 0, and 1. So then we'll do 0 times our -1 to the 1 plus 2 for our I and j, and we'll use these entries for our submatrix when we're multiplying by 0, or right here, 2, 4, 1, 1. And then our last coefficient is 1 times -1 to the 1 plus 3, and we will be using those entries for our submatrix. Now we can compute the determinant, and the 0 term will vanish since we're multiplying by 0. So after doing that, we'll have -1 plus 0 minus 2, and that is equal to -3 for our determinant. Now we multiply by 1/2, so 1/2 times -3 is -3/2, and then we multiply by a negative to make our answer positive since area is positive. So -1 times -3/2 will give us positive 3/2 square units. So that is the area of our triangle. Now here we're given another example, which you can go over to practice. Now to test if 3 points are collinear, that is to say that those 3 points lie on the same straight line, we need to check if the determinant of a 3x3 matrix that we construct from those 3 points is equal to 0. So first, we let our first row be the x coordinates, so our x1, x2, and x3. Our second row of our 3x3 matrix will be our y coordinates, our y1, y2, and y3. And our last row will be all 1s. Now, those 3 points will be collinear if and only if the determinant of the 3x3 matrix we constructed is equal to 0. Now, to construct an equation of the line through 2 distinct points, we can once again construct a 3x3 matrix where our first row will have our x variable, then our 2 coordinates, our 2 x coordinates, so x1 and x2. The second row will have our y variable, so y, then our 2 y coordinates, y1 and y2. Then our last row will have all 1s. And then we can compute the determinant, and since we have our x and our y, we'll have an equation. So we'll set that equation equal to 0, or set our determinant equal to 0, and that'll give us the line that'll run through the 2 points x1, y1, and x2, y2, and we'll be going over some examples. For our first example, we are checking to see if the 3 points provided are collinear. So we construct our 3x3 matrix, our first row being our x coordinates, so -2, 1, and 7 right here. Our second row being our y coordinates, our -2, 1, and 5, and then our last row being our 1s. Now, once we compute the determinant of that 3x3 matrix, we get a determinant of -6, which is not equal to 0. So that means that the 3 points are not collinear, and we can see that by the points that are graphed, or that are plotted right here to the right. Now for our second example, we are told to find the equation of the line passing through the points 2, 4, and -1, 3. So for our first row right here, we write our x variable, then our x coordinates 2 and -1, 2 and -1. Our second row, we write our y variable, then our y coordinates 4 and 3, and then our last row is our all 1s. Now we can compute the determinant of this 3x3 matrix, but it will be in an equation form since we have the variables x and y. So using the cofactor expansion, first we're using our x, so we'll be deleting this column and row. So x right here times this submatrix right here. Now minus 2, since that is our second entry in the first row. So 2, so that means we'll be deleting this row and this column, and we'll be left with this matrix right here, this submatrix, the y, the 3, and the 1, and the 1. And then our last entry is minus 1, so minus 1 times this submatrix right here, right here. Now we can compute the determinants of the submatrices. So 4, for the first one, 4 times 1 minus 3 times 1, so 4 minus 3 will give us 1. For the second one, y times 1, so y minus 1 times 3, so y minus 3. And then for the last one, it'll be y times 1 minus 1 times 4, so that'll give us y minus 4 right there. Now we can simplify the 4 minus 3, and that'll be 1, so we'll have x times 1 right here, and then we'll have negative 2 times y and negative 2 times negative 3, and then we can distribute the negative into the y and the negative 4 right there. So now we can combine like terms, and we'll have an equation of x minus 3y plus 10 is equal to 0. So that means that the equation of the line that passes through the points 2, 4, and negative 1, 3 is given by that equation that we just found. So now for a quick recap, we were able to see that the determinants of these matrices allowed us to solve the systems of linear equations. So when we had those 2x2 matrices, we were able to use Cramer's rule, and I believe even we did a 3x3 matrix. We were also able to find the area of a triangle, test for collinearity, and we were able to see if, we were able to compute the line that passed through 2 distinct points. So lastly, the determinants of matrices have an application in cryptography. So cryptography is the science of securing information so that only intended recipients can read it. So it uses mathematics, so some portions of mathematics include matrices, number theory, and algorithms. It ensures confidentiality of messages, and it is widely used in email, online banking, and data security. So for the Hill cipher, it uses a square key matrix K to encrypt and decrypt blocks of letters. So for encryption, we convert the letters to numbers. So A is equal to 0, B is equal to 1, up until Z is equal to 25. Then we can group into column vectors of size n. So C is equal to K times P, where P is the plain text vector and C is the ciphertext vector. And we divide by 26 and keep the remainder. So that's what the mod 26 means. So for decryption, we take the inverse of K and we divide by 26 and keep the remainder, so the mod 26. And P will be equal to the inverse of K times C mod 26. And this works only if the determinant of K is a relative prime to 26. So an important thing to note is that if the greatest common denominator of the determinant of K and 26 is equal to 1, then K inverse exists modulo 26, and decryption is possible. So the mod 26 just ensures that all the numbers that we calculate will range between 0 and 25 because that is what we labeled our letters. A is equal to 0 up until Z is equal to 25. So for the role of the determinants, the determinant of K tells us if the key matrix K is invertible, if the greatest common denominator of the determinant of K and 26 is not equal to 1, then K is not invertible and the message cannot be uniquely decrypted. So this guarantees a one-to-one mapping between plaintext and ciphertext blocks, and it provides the foundation for secure and reversible encryption. So here I'll go over the first example. We are told to encrypt the message ACT by using the key matrix K is equal to the 2x2 matrix with entries 3, 3, 2, and 5. So first we convert the letters A, C, and T to their respective numbers. So A is equal to 0, C is equal to 2, and T is equal to 19. Now we can group them into column vectors of size 2. So P1 is equal to 0, 2 for the A and the C. And P2 is equal to 19, and then we'll pad with an X since we don't have another letter. Now for X, we will let it equal to 23 because that's its number form. Now we need to check if K is invertible, mod 26. So we first compute the determinant of K. So 3 times 5 minus 2 times 3. So 15 minus 6 is equal to 9. So now, in order to check if it is invertible, we take the greatest common denominator of 9 and 26. Sorry, the greatest common divisor. And that is equal to 1, so that means that the inverse of k exists. Now we can encrypt each block. For c is equal to k times p. So we'll do matrix multiplication for c1. So we'll have k times p1, so our matrix k, times our first column matrix, the 0 and the 2, and we get the matrix 6, 10, and we take the mod 26. So 6 divided by 26 gives us a remainder of 6. So 6 divided by 26 is equal to 0 with a remainder of 6. Now 10 divided by 26 is equal to 0 with a remainder of 10. So for the first column matrix, we have 6, 10. Now for C2, we multiply k times P2, and we get the matrix 126, the column matrix 126 and 153. So 126 divided by 26 will give us a remainder of 22, and 153 divided by 26 gives us a remainder of 23. So now we can convert those numbers back to letters. So 6 and 10 will be G and K, and 22 and 23 will be W and X. So now our ciphertext is GKWX.